continue. So our next speaker is Martin Zeller. He will talk about rethinking chiplet design for next generation ADAS applications. And quick intro to Martin. Martin is responsible for a team of 70 engineers building complex SoCs, mainly in the area of ADAS and MSIC. Stage is yours.
Thanks. Welcome. Yeah, so when I created the slide some days ago, I was thinking if I'm maybe too pessimistic and looking at the requirements of our potential customers and customers. But hearing the keynote this morning, I said, oh, maybe I'm too optimistic, because I think we have Moore's law, and we are somehow all used to cope with it. But what we are currently seeing is that the technology is staying a little bit below Moore's law, not scaling that good anymore. But the customer demands are way above Moore's law. And so I think we need several methodologies to cope with that. And cannot do only one thing. Yeah, chiplets, everybody thinks chiplets is great. It's great. Same as for AI, yes. That's a great help. But will it be enough? I would guess no. What did I do? Yeah, so I will talk a little bit about complexity, mainly from the point of view from DreamChip. So it's not overall valid, but just an exemplary approach. I will talk about our platform approach. And of course, in the end, I will have a success story. Maybe showing some chips. So one chip we did, this was 2022. So you see it's still pretty tiny. Then the year after, it's getting bigger. And last year was even 3 times bigger. So I did a SoC complexity graph here. My engineers always tell me, hey, that's way too simplified. But in the end, still, you see it's a logarithmic scale. And yeah, we are going up pretty fast. And I said, I'm here at a factor of 1,000. I think seen this morning in the keynote, he was at 10 to the power of 3 up to 10 to the power of 6. So maybe I'm even factor of 1,000 below reality, not sure. And yeah, so what's the issue with that? Yeah, we increase the complexity by a factor of 1,000, fine. But nobody will give us the time and say, okay, so far a project needed 1 year, now we have 1,000 years. No. We will not even get twice the time, probably, but we should stay in the old schedule or even faster. And yeah, I think for that we need some new ideas, because coping with that gets tricky. And so how to cope with this 1,000? Chiplets, yeah, good idea. How many chiplets can I put in one package? Order of magnitude? Yeah, it's already there, but I would guess more than 10 gets tricky. At least not 100, because you need to connect them somehow. One of the biggest problems. You need a huge space die in the middle where you can connect all the peripheral chiplets. And yeah, so I think a factor of 10 currently is realistic. Then, just in the last presentation and also in others, and also the topic of this track, AI. Yes, it will help. It will make chip design faster, easier, maybe safer. But how much will this bring? Yeah, engineers like to think in orders of magnitude. So I said, okay, technology, tools, AI, it will maybe give us another factor of 10. And yeah, now another 10 is missing. So yeah, what do? We said, yeah, let's build a platform and not then let's handle all chips we build as derivatives. not as development from scratch, but as just a change in an existing chip, what is way faster and takes away a lot of risk and effort. Yeah, very short, except to chiplets. I think we've heard a lot about this today already. Of course, we can scale with this, we can mix and match. We can use the right technology for every chiplet. An I/O chiplet, maybe in an old technology, a computer chiplet in a new technology. We can, of course, increase the yield. We can do reuse. But as said, maybe an X10, not an X100. Then what's the idea of the platform? So for the platform, of course, we can reuse chips or chiplets, whatever. So not too much difference if I connect two chiplets by UCIe or two chips by PCIe. Yeah. We can do it on the level of hard macros. So if I have macro and I do the next design, use the same one, I'm pretty sure that the chip will work, or that this block at least will work. I can do it on subsystem level, just building generic subsystems, or going up, doing only IP. That's what everybody is doing today anyway, I would say. Buying IP and building chips from IP. Nobody will design a whole big SoC from scratch. But also the concept can be part of a platform. So very abstract, just as you said, who will write the specification? Will this do the AI? Probably not. So even the concept can be part of a platform concept. Of course, reuse of a concept is the concept is very flexible, but the reuse will be best if I have a chip and just take it and put it on the board as is. On the other hand, or the same is true for the software, because yeah, we are all chip focused, and we say, hey, great, we are ready with our chip. Then people come and say, yeah, and now we need 10 times the effort for software. And I think there have been a lot of AI startups who build great chips, and then NVIDIA comes and says, hey, we have a solution of software and chip. Then all these great startups are out of business because nobody wants to spend the software. So I think that is a huge differentiator if you have a platform, a system of chips that runs with the same software as the generations before, and the software is ready or halfway ready. Another thing is functional safety. You know, for others, with every half level you raise in autonomy, functional safety gets more and more severe. And of course, you can do it from scratch every time, but having something ready again saves a lot of effort. And in functional safety, you have this concept of proven in use, proven on silicon. If you can say, hey, this part is used, it's running in 10 million cars already, then it's very easy to get a check mark from a certification authority. So everything you reuse, you will also save effort on functional safety. Again, the same as the spec. Once you have done your requirements, your specification, you can reuse parts of that. That's a big plus for your functional safety certification. Of course, there's a plus, there's always a minus. Flexibility is very high if you just have a concept, and it's very low if you have a chip ready. So what to do? Do we need flexibility or do we need reuse? Yeah, let's keep the flexibility for the stuff that really makes our product, for our key selling points, for a differentiator. And let's do the reuse for the stuff that nobody cares about. Who would say, hey, you have a very nice USB interface. Great, I will buy this chip. Nobody. We'll just say, oh, USB checkmark, fine. But if you have something very special, differentiator, that's something that it makes sense to build your own, to change it, to build something new into your chip. But all the legacy stuff, interfaces, debug trace, whatever, CPU, even control CPU. Yeah, there's a CPU. Some people like ARM, some people like RISC-V. But in the end, yeah, it's a CPU. Nobody will buy this chip or that chip because of that. So I think it's very important to think what do you need to be changed and what can just be from the platform as is, fully specified, fully functional safety certified, with software that is running. And what is really a differentiator? I need to change something. Yeah, so we've built this platform 2 years ago, trying to think what do you usually need in a ADAS context. So, okay, probably you need some data crunching with high bandwidth to the memory, with high compute load. So here we took 2 different AI engines from Cadence and from the university. Then you need a control processor. Yeah, you need somebody controlling the interfaces, the data flow, and so on. In this case, we took an ARM A-core split lock mode so that you can decide do I want safety or do I want performance. A NOC, very important especially for bigger chips, a NOC concept that connects blocks with maybe 10 millimeters run length, what is then not that trivial anymore. DDR memory, okay. I don't like it. I always try to push my people to do everything with SRAM and to optimize, but it's not always possible, especially if you're in the range of radar or image processing. Yeah, then you need all the nasty housekeeping stuff. PLLs, clocks, power, Q channels, reset control, temperature control. Nobody wants to bother with that. You just need it, and it needs to work. And once it's set up, probably you don't want to touch it ever again. Same for debug and trace. It just has to work. Nothing to differentiate. Standard IOs, the same. UART, SPI, GPIOs, yeah, has to work. Software trials have to be there. Nothing to differentiate. High-speed IOs, the same. Ethernet and PCIe we have here. Platform. Streaming data, pretty important, also for the NOC and memory layout, let's say, because this is stuff you cannot stop. If the camera is sending MIPI data, you have to take it. Okay, 5 minutes. Yeah. Yeah, and last but not least, safety and the secure boot. So, yeah, that's also something for ADAS. Usually, you need somebody controlling the safety, and you need a secure boot, authentication, decryption, and some safe interfaces handling all the automotive stuff. Then a year later, we built a derivative, as said. We are not building new chips now. We had a customer asking for a chip, and we said, yeah, let's build a derivative of our platform because it's just faster and cheaper. So yeah, what did we change? So we put in some new DSPs for radar processing. We updated the ISP to the latest version. We added some Ethernets and PCIes, just doubling up the head macros, not even touching them, and added some synchronization logic to the low performance IO, some more memory. Yeah, sounds all easy. And so that's what we achieved. Pretty big chip, more than 200 square millimeters and 22 FDX, manufactured in Dresden. And we did this all in 7 months, from the PowerPoint idea to the test chip tape out. I think this is a pretty impressive schedule for such a chip. And if you think about it, developing it from scratch and having a lot of people discussing, do we take the A65 or do we take the A53 or do we take the A72, which is best? So I think also for this, all these concept discussions, it's a good thing if it's just there. Yeah, we can change it, but it's 3 months extra. Okay, not at a point. And yeah, so I think with this concept, you can really build chips faster. ARM is also jumping on it now. I think they are thinking a lot, at least about subsystems to build and following a, I would say, similar idea now. Yeah, and then I'm at the end. Any time? Perfect timing. Yeah, so yeah, I think we need to keep schedule and budget under control with the more requirements from the customers. And we need various methodologies. We cannot rely on one of them. We just need to combine all forces to do this. And at least in this case, we've shown that we can do so. And yeah, just last week, we started the next chip project that is, again, a similar schedule. Let's see and hope for the best. Thank you.
Thank you for the talk. We have a bit more than a minute left for questions. We can start with questions from the room. You.
How much does the expense scale? I hope it's not times 10 chip with usage. How much does the expense, the cost of the chip scales?
Good question. So as long as you're going with this technology, probably IP is the biggest expense you have to do. If you go to smaller technologies, it's a mass cost. So it's very hard to say. Sorry.
With cutting edge. Novel technology, what would be your estimate?
Oh, that's a good question. So we've seen the slides this morning in the keynote with expense for the different technology steps, but I would say the effort for the chip design is the lowest part. So the engineering, we are cheap, comparable. But I think the correct question is, how big is the probability that you get your money back? And it's bigger if you have your chip ready in half a year than if you have it ready in 2 years. That's maybe the not so direct answer. Sorry.
Okay, that's perfectly on time. Thank you, Martin, again.
Thank you.